Hello, welcome to the video. In this lesson, we're going to be looking at section 3.7, where we're going to be graphing absolute value functions. So anything that has an absolute value uh, in the function classifies as an absolute value function. And with using the same methods to graph a linear function, we're going to attempt to do some of those things in order to graph an absolute value function. But before we kind of get into what the process is in graphing, the first thing we're going to do is look at what a graph looks like when it is in an absolute value function. So when you notice on the graph here shown, the graph appears to be like a V-shaped. So it's over here, it comes down, it has a stopping point, and then it comes back up in this particular instance. This specific graph is the function f of x is equal to the absolute value of x. Now, every single absolute value function is going to have a vertex, okay? So the vertex is going to be an indicator on where the graph is going to go. And in this case, the graph will be going this way, and the graph is going to be going that way. The reason for that is this. Let's say we were going to make a table using f of x is equal to the absolute value of x, but I'm just going to change it to y is equal to the absolute value of x. So let's say I picked some values for x, like -2, -1, 0, 1, and 2. And I placed them in to the equation or function. So the absolute value of -2, we know it's going to be positive, so that's 2. Absolute value of -1, this is going to be +1. Absolute value of 0 is 0. Absolute value of 1 equals 1. And absolute value of 2 equals 2. So I have these series of ordered pairs. The ordered pairs become -2, comma 2. This is -1, comma 1. This is 0, comma 0. This gives us 1 comma 1, and this gives us 2 comma 2. So if you notice, if I were to plot these points on the graph, -2 comma 2 is right here, -1 comma 1 is right here, 0 0 is right here, 1 1, 2 2. All of the points that I made on the table fit on this graph. So then I can say, okay, this is where the change is, where my vertex is, and I can draw it from there. Okay. Sometimes discovering what the vertex is may be an easy task. Sometimes it is not as easy of a task. So what I want, what I want us to hone in on and identify is really, I only really want you to pay attention to graphing the function. I'm not as concerned about you comparing. I'm not as concerned right now about you describing the domain and range. I really want you to understand how to graph the function. And so looking at these two examples, I got g of x is equal to the absolute value of x plus 3. And for part B is the absolute, m of x is equal to the absolute value of x minus 2. So the one thing that you have to keep in mind is what is being considered with the absolute value. Is it one term or is it several terms? In this particular instance, there's only one term that's inside the absolute value, and that's x. if you look here in B, we have two terms. We have x and we also have the minus 2. Okay, so that does change things a bit when we are looking at our graph. So if we were to make a table, so I have my table here, and I'm going to plot points for this particular example. So if x was 0, here I'll just make my table right here. If x was 0, y would be 3 because 0 plus 3 is 3. If it was 1, it would be 4. If it was, let's say, negative 1, it would also be 4. So I'm just going to plot those points. So I got 0, 3, which is right there. I got 1, 4, 1, 2, 3, and I have negative 1, 4. So if you notice, I have a change in my graph, and it appears to be that my vertex is located at 0, 3. So that's where it gets changed. So it looks like my graph is going to go here, and it's going to go here. So that is the graph of g of x is equal to the absolute value of x plus 3. Okay. Now, if I were to look at example B, and it says x minus 2 is inside the absolute value. So what I'm going to do is I want to use what's inside there and illustrate, okay, what is going to make the inside of that absolute value 0? Well, in this particular instance, it's going to be 2, because 2 minus 2 is 0. So if I put, let's say, 2 right here, let's say I put 1 here, and let's say I put 3 here. More often than not, what makes the inside of the absolute value 0 is going to be the location of the vertex. So I am betting on where x is 2 is going to be the vertex, and then 2 minus 2 is 0, absolute value of 0 is 0. If I put 1 in here, 1 minus 2 is negative 1, absolute value of negative 1 is 1, so it's 1 comma 1. 3 minus 2 is 1, absolute value of 1 is 1. So I got 2 comma 0 right here. I have 3 comma 1. I also have the 1 comma 1. All right. I was correct by identifying x being 2 as the location of our vertex, and this is how we were going to graph our absolute value function. Again, same idea, looking at trying to be able to graph these. Let's take a look at number 1, h of x is equal to the absolute value of x minus 1. What makes the inside of the absolute value 0 for x? It's just going to be 0. Well, if I took the absolute value of 0 and subtracted by 1, I get 0, comma, negative 1. So that's where that point gets plotted. So where I just plotted that, that's going to be my vertex. Now, if I said, let's say I put negative 1 in for x here, absolute value of negative 1 is 1. 1 minus 1 is 0. So negative 1 comma 0 is right there. Absolute value of positive 1 is still 1. 1 minus 1 is 0. And that's what I got right there. And so this is how we would graph this particular function. Going to look at number 2. It's got the absolute value of x plus 4. So what makes the inside of that absolute value 0? Well, x would have to be negative 4. So negative 4 plus 4 is 0. That's going to be my vertex. So negative 4 comma 0 is my vertex. If I went uh, an x coordinate to the left, which would be like negative 5 plus 4 is negative 1. Negative 1 absolute value is positive 1, so I get negative 5 comma 1 is a point on the function. And if I went to the right, I got what, negative 3? Negative 3 plus 4 is 1. Absolute value 1 is 1. And this would be my absolute value function for um, n of x is equal to the absolute value of x plus 4. So up to this point, we have looked at a series of absolute value functions where we made a right side up V-shaped graph. But let's take a look at example B, for instance. Example B is going to be an indicator that we are going to have a graph that is not going to be a right side up V shape, but it's going to be an upside down V shape. And the reason why is that outside negative 1/2. So, for instance, let's say I still use the same practice of figuring out, okay, what's going to make the inside of my square root, or not square root, inside of my absolute value 0. In this case, it's still 0. But if I took 0 times it by negative 1/2, I get 0. So 0 comma 0 is my location of the vertex. But now let's say I picked a value of positive 2. Absolute value of positive 2 is 2. 2 times a negative 1/2 is negative 1. So 2 comma negative 1 gets plotted here. Now, if I use negative 2, absolute value of negative 2 is positive 2, and positive 2 times by negative 1/2 is also negative 1. So because of that negative 1/2, my absolute value function now becomes an upside down V shape. And so that's where the negative comes in. When we write an absolute value function in standard form, more specifically, they call it vertex form, this is how it looks. They have it here, it says g of x is equal to a times it by the absolute value of x minus h plus k. There is a lot of terms there, and what we're going to do is kind of dissect this function and show you how we can graph this without necessarily making a table. So let's start with an example. So again, here, all I want to do is graph the function. I'm not concerned about comparing. So let's look at this value here. So it says f of x is equal to the absolute value of x plus 2 minus 3. All right, let's go back to that general function. G of x is equal to a times it by the absolute value of x minus h plus k. So there are a series of steps that are going to help us solve this equation easier than just putting it into a table, because you could certainly put it into a table, but because of all of the values and all of the terms that is placed there, it can get a little bit messy in the calculations. So here's what we're going to do. So it has a series of steps. So let's look at step 1. Step 1 is we need to figure out what A, H, and K are with respect to the original function. So A is going to be equal to 1 because there's no value on the outside of my absolute value. That just means it's represented as 1. H is always going to be represented as the opposite of how it appears. So since it's x plus 2, h is actually going to be negative 2. And then k, because it's plus k, it's always going to be represented as is because so since it's minus 3, it's going to be negative 3. So h is 1, oh, I'm sorry, a is 1, h is negative 2, and k is negative 3. So that's the first step. Step 2, we need to identify the vertex. The vertex is going to be the values of h comma k. Well, h is negative 2, so and k is negative 3, so my vertex is going to be located at negative 2 comma negative 3. So let's plot that point. So negative 2 comma negative 3 is right there. Now, the next one, the next step, I like to call it finding the slope. And the slope comes from a. So in this case, since a is 1, your slope is going to be 1 over 1. So I go from my vertex point, and it's rise over run, so it's up 1 to the right 1. Plot that point. And then the final step, step 4, we are going to look at what is called a mirrored image slope. And all this means is this. The top number remains the same, so it's positive 1, and whatever the bottom number is, tag a negative to it. So in this particular instance, my mirrored image slope is going to be 1 divided by negative 1. So I go up 1 to the left 1. And what should happen is you should have your vertex and then 2 points that indicate that where my V shape on the graph is going to be. Since A was a positive 1, that means it's going to be right side up, so it's consistent with the equation. And then I just connect the points from the vertex. And so this is how we can graph f of x is equal to the absolute value of x plus 2 minus 3. Let's look at the other one. So here we have g of x is equal to 2x plus 2, and then it's minus 3. All right, so now let's take a look at the second example here. So we have g of x is equal to the absolute value of 2x plus 2 minus 3. Okay, here is what is different from this example to standard form. If you notice, there is no value attached to x, and that there so happened to be a value attached to x here, which is 2. So what we're going to do for this one to identify the vertex is I have to figure out if I can factor this out to get x by itself. So in this particular instance, I can say that g of x is going to be equal to 2 times by the quantity of x plus 1, and then on the outside is the minus 3. So what that means is my vertex as of h is going to be negative 1, and my value of k is still negative 3. So negative 1 comma negative 3 is going to be my vertex. Now, unlike what we did up here with the steps 1 through 4, my slope in this particular one is actually going to be the reciprocal of what is inside our absolute value. So 2 is the value that is on the inside of the absolute value. That means that my slope that we were going to look at is going to be the fraction, or that fraction is going to be flipped, so it's going to be 1/2. So that means I'm going to go up, looks like it's going to be up 1 to the right 2. Oh, sorry about that. I messed up. It's still going to be that slope here. So it's still going to be 2 over 1. So it's up 2 to the right 1, and it's up 2 to the left 1. And that is our graph for that specific one there. All right, let's take a look at question 6. So I'm graphing this function here. So I have f of x is equal to x plus 2, and then, or the absolute value of x plus 2, and then plus 2. So find the vertex. Vertex is going to be h, which is -2 in this case, and k is +2. So -2, +2 is up here. A is my slope, so it's up 1 to the right 1, mirrored image slope up 1 to the left 1. I have my graph for the absolute value function there. When I'm graphing the second part, I have g of x is equal to the absolute value of -4x plus 2, and then it's plus 2. So like I did in the previous example where x was not by itself, we needed to solve this as a value of x just by itself. So it was going to be g of x is equal to the absolute value. I'm just going to put -4 here, and then it's going to be x no, it'll be minus 1/2, and then plus 2. So here my vertex is going to be at +1/2 comma 2, which is right here. And now with this particular one, it's tricky because uh, on the inside it's still a -4, but because you could take it out of the absolute value, it turns into a +4. So my slope is still going to be +4 over 1. So 1, 2, 3, 4 to the right 1. And mirrored image slope would be 4 to the left 1. And this is where we would get our function from there. All right, so final graph that we're going to look at is this one here. This one here shows a graph that's more in standard form because you have the x by itself. And again, I just want to graph it. So in this particular one, my vertex is going to be located at +1 comma 3. So I plot the point there. A is on the outside, which is -2. So my slope is going to be down 2 to the right one. My mirrored image slope is down to the left one. Because -2 is on the outside, that means this is an indicator that we have an upside down V-shaped graph. And that is being able to graph absolute value functions. Hope this helps. Till next time.